So up to this point, we've been talking about all these concepts that pertain to the derivative pretty informally. So now we want to kind of formalize it all. So we want to actually define all of these things and look at the actual formal definition of the derivative. Okay. So just starting with a few definitions here. First, the definition of the tangent line. Okay, so the tangent line at a point x equals a to a function f is the line which intersects f only at the point a f of a. Okay, so it's the line which intersects this function only at this point. Okay, now this could be harder to visualize for some functions, like for example a line, right? It's not really even possible to do that. So we don't always necessarily think of the derivative as the slope of the tangent line. But for most cases, it's fine. It's really only going to fall apart in cases like, well, I shouldn't say it falls apart. It just looks a lot different. So you can do it with a line. It looks a lot different than it does for the x squared. So I guess I kind of take that back. So all I meant was if we have something like x squared, right? So we saw that the slope of the tangent line at this point, it looks something like this, right? Where it's going through it, it's only crossing at that one point. But if you have something like a line, it's going to look a lot different. Okay. So the slope of the tangent line, it's going to look, it's just going to be that line, right? It's just going to be like the line over itself. So it kind of falls out of this definition. So it's better just to use this definition for curves, where it's only intersecting at one point. It kind of falls apart when you're looking at other lines or like a horizontal line or something. But it won't really be an issue for us because these functions will be a lot easier to find the derivatives of anyway, because we're looking for the slope, which is the same at every point, right? So these are kind of the things that we're trying to develop a new kind of system for, right? We can use the old systems for these. So for the curve, any kind of curve, we would define the tangent line this way. Okay. So now let's go ahead and define the derivative. So the derivative at a point A of a function f is the slope of the tangent line to f at A. Okay, so you find the tangent line and then you find the slope of that tangent line. So again, the tangent line definition works better for curves. So if it's just a line, it would just be the slope of that line, and the slope is the same at any point. So we can think of it the same way, essentially. So this, of course, is just the definition of what the derivative means. It doesn't tell us how to actually find that derivative, right? Before we do that, though, let's just note here that the process of finding a derivative is called differentiation. Okay. So this is where we get the idea of differential calculus, right? So we call this process differentiation. So if we were to say we want to differentiate a function, it means that we want to find the derivative of the function. So we already saw kind of that we are going to find this derivative using limits. So naturally, limits don't have to exist. So this means that the derivative also does not have to exist, right? So we'll look at those situations next. So let's go ahead and write out the limit definition of the derivative first. So this is how we would actually find the derivative. So let f be a function defined in an open interval containing a. So you might recognize this as the opening of the definition of a limit. Then the tangent line to f of x at a is the line passing through a f of a having slope m, maybe we write m tan, equals the limit as x approaches a of f of x minus f of a divided by x minus a. Okay. So this is sometimes known as like the alternative definition of the derivative. This is a little bit different than the one we looked at using h, which is the more common one that I'm going to write down in a second here. But this shows that we can essentially, we let x get closer to a, so we let x approach a, converge into a, and that will, this is the slope of the secant line between x and a, and this will give us the slope of the tangent line once we take the limit. Okay. So of course this is dependent on the limit existing. So there need not be a tangent line, which means that there need not be a derivative, right? And this definition of the tangent line, it'll work for curves and lines and everything. So this is a little bit more of a general definition of that tangent line, where the other one's more of like an intuitive definition. Okay. So equivalently, we like to reparameterize this in terms of a and a point a little bit to the right or left of a, and then allowing the distance between those points to go to 0. Okay. So let's say we may define the tangent line of f of x at a to be the line passing through a f of a and having slope write it down here so it's kind of on its own. M tangent is equal to the limit as h approaches 0 of f of a plus h minus f of a divided by h. Okay, so this is the one that we saw before. The bottom would be a plus h minus a, and the a minus a would cancel out, and then you're just left with h. And this is the one that's typically easier to work with algebraically when we find these limits. Again, if you plug in the limit, you get, like if you do direct substitution, you get 0 over 0 in indeterminate form. So that tells us that if we do some algebra, we might be able to actually get a value for that limit, provided it exists. Okay, so that's kind of how we're going to want to tackle these. Now, here we're just defining specifically the slope of the tangent line and also therefore the derivative at a point. So now we want to come up with a definition for the derivative function. Okay. So a function for the derivative, which is defined at every point where the derivative exists. So a general kind of equation, right? So maybe there's an equation that describes the derivative at every point of x squared, for example. So how do we come up with that equation? Okay, so the definition here is that we let f be a function, then the derivative function f prime, what we could call it, is the function whose domain consists of those values of x such that the following limit exists. Okay, so this is f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x divided by h. Okay, so again, the bottom is really like x plus h minus x, but the x's will cancel out. So we're just extending that definition of a derivative at a point to the definition of a derivative for any point x, and this allows us to come up with the general definition of a derivative. So we can then go ahead and find this limit, and it will allow us to find the derivative of a function. So just to go ahead and test it real quick on an easy one, okay, what would an easy one be in this case? Well, what about the function f of x equals 2x, right? We know that the derivative of this should be 2 because the derivative is the slope of the function, and the slope of this function is 2. So, and it's 2 everywhere. So the general definition f prime of x should be 2. So does this function, does that give us 2? So let's go ahead and see. So f prime of x is equal to the limit as h approaches 0 of x plus a, f of x plus h. So this is going to be 2 times x plus h minus 2x over h. Okay, So just using the function composition here, putting in x plus h for x, and then f of x is just 2x. Again, if you go ahead and do direct substitution of the limit, you're going to get 0 over 0, right? You'll get 2x minus 2x, which is 0 over 0. So we'll go ahead and simplify the top. So limit as h approaches 0 of 2x plus 2h minus 2x over h. Okay, 2x and 2x cancel out. So we have the limit as h approaches 0 of 2h over h. Well, here the h's cancel out. So you have the limit as h approaches 0 of 2, which is, of course, just 2. Okay, so we do indeed get what we would expect to get here. Okay, so again, the derivative doesn't have to exist. Remember that for a limit to exist, this needs to, the left and the right hand limit need to both exist, and it needs to not be infinite. So we'll see some examples a little bit later where derivatives do not exist. But for now, so the next thing we'll do is we'll look at some different examples of how to find the derivatives of functions using this definition.